Good afternoon, everyone. I'm Riwei from City University of Hong Kong, and I'm so delighted to present my work, UnICom, a universally high-performance I/O compression mechanism for modern computer systems. Modern computer system evolution provides many advanced storage technology. For example, like some emergent SSD that provides over millions of IOPS and near 5 microsecond I/O latency. But for the traditional I/O stack, particularly for the linkless I/O stack, it can contribute over 50% software overhead of the total I/O latency. So such high overhead motivate us to design an efficient I/O stack for existing storage system. And in addition, modern computer system also we also observe many real-world workloads that include different types of workload. For example, like the pure I/O workloads and mixed workloads, just like the figure shown below. And so in this paper, I'm focused on the I/O compression mechanism optimization on the different types of workloads. So let's get started from the dilemma of interrupt and polling. I think there are dilemma or trade-off of interrupt and polling have been introduced in many previous work. I remember that there's a work DAPS, if I remember correct, presented yesterday. It is another excellent work to optimize the I/O compression mechanism. But for this paper, we try to optimize this dilemma in another direction. We start from some case study, and we try to evaluate these two I/O compression mechanism with two representative words. The first one is ext4 for interrupt and bypass D for polling. And we also evaluate these two cases on two different workloads. The first workload is pure I/O workload, and another one is mixed workload. And the mixed workload means that the I/O swaps and the compute intensity swap, they could be one in the same system or same computer. And so that they will intensively compete for CPU resources, and resulting in some mutual interference. But in our experiments, we use counter swaps to represent C swaps, where the counter swap means that we will create a swap, and its task is just to count some value. So the count value of these swaps during a period in the case is computational performance. And if we have multiple counter swaps, the sum of counter value of the counter swap also means there are computation performance. And so for the last slides, I will use C sharp to represent counter swap because it represents a special case. And so for the performance on pure I/O workloads, for example, like the result shown in the figure, interrupts of course shows the low I/O performance due to the high software overhead and the high cost sleep wake up routing they will use in their compression mechanism. And another one is polling. Polling of course shows a higher IOPS than interrupts, especially when the device is not saturated. But we make another observation for 128 KB IOs, as the figure shown at the left side. We will see that if the SSD is saturated, of course, because the IO will be killed by the devices, so their IO latency would increase. So, but for the polling approach, the increasing IO latency in polling means that they have to do more busy waiting here and wasting more CPU cycles. So this one of our observation. And in this observation, when we switch the CPU utilization to high CPU utilization, we can see that we have totally different observation. And for example, like for interrupt, we can see that the interrupt shows higher IOPS performance and C-sharp performance in high CPU utilization, as the green box shown below at the right side figure. But for polling, we can see that polling shows lower IOPS performance, C-sharp performance than interrupt. because because they will firstly they already saturate the devices and the polling, and they will have some mutual interference effect with 4 kbIO. So we will see that the 4 kbIOs also, the IOPS performance of 4 kbIOs also decreases. And for 128 kbIOs, the C-sharp performance will continue to drop because the observation we make in the previous slides, that is the longer and longer IO latency and wasting more and more CPU cycles. And so we identify the root cause of this. The root cause is the per-thread polling increase the CPU contention because in the synchronous IO scenario or blocking IO scenario, which is a very common IO mode used by many real applications, and each IO step has to poll for the IO, and if there are many IO steps, poll for IOs and poll for big IO, they will wasting CPU cycles each by each, so totally wasting more and more CPU cycles, making the CPU utilization inefficient. So, and to address the issue of per-thread polling, my first observation is that maybe we can use the asynchronous IO framework like IO-Ring in SQ mode to address this issue, because for the IO-Ring in SQ mode, it will create a submission step. This submission step will receive IO requests from different applications, and they will help applications to check the IO completion in this centralized submission steps, so we can so that we can transfer the per-thread polling into a centralized polling to reduce CPU utilization. But it also has some limitation here. The first limitation is about the incompatibility, because IO-Ring as a synchronous IO framework, it requires application that only supports synchronous IO to change their source code, because they have different IO paradigm. And another one is the performance bond. It is because for IO-Ring, it still relies on the underlying kernel completion mechanism, for example, like the interrupt to finish the IO, so that it will also suffer from the similar software overhead like the interrupt-based approach. And the last one is the limited multiple process support, because for the IO-Ring, if we create each submission step for each process, the per-thread polling issue will be transferred to per process polling issue, and it do not fundamentally address the issue of inefficient CPU usage. So our design goal is to design an IO completion mechanism that delivers universally high performance across different scenarios, including the linear polling IO performance in pure IO workloads, or we refer to low CPU utilization, and near interrupt IO performance and C-sharp performance in mixed workloads or high CPU utilization. Of course, we need to support synchronous IO because we want to transparently support existing application. They do not need to rewrite any source codes. To achieve this goal, we encounter some challenges. The first challenge is how to achieve a linear interrupt performance. Because if we want to make the CPU usage efficient, I think we need to design an interrupt-like sleep and wake up mechanism, because we always want the CPU can do other tasks when the IO is not finished. But based on our observation, existing task deactivation or reactivation operation, or for example, like if we want to, if the IO leads to is submitted, the task goes to sleep, and this task should be in queue, should be dequeued from the CPU's 1 queue or in queues to the CPU 1 queue. And this operation, we noticed that it contributes around 33% software overhead of the total IO latency. So this creates a heavy sleep and wake up overhead. And the second challenge is about the linear polling performance. and the synchronous I/O. Because we want to save CPU efficiency while ensure high I/O performance. So we inspired by the I/O ring, we still want to consolidate the per step polling into the one polling steps, but we have to address the limitation of I/O ring. So that's another challenge. And the second one is to reach lower and lower software overhead. This is because we, based on our observation, the kernel bypassing I/O have proven that the kernel bypassing I/O can significantly reduce software overhead. So we want to adopt this design. So the last challenge is to challenge 1 and 2 while safely and efficiently support kernel bypassing I/Os. So let me introduce my insight. My insight is from an observation of an I/O latency breakdown. We noticed that system call for most reaching between user space and kernel space is no cost, about 1.7%. This overhead, I think this overhead is worse if we trapping into kernel to leverage kernel infrastructure to overcome tranche 1 and 2, and it is worse. And while if we can kernel bypass most of I/O stack to overcome tranche 3, and I think it would be a possible solution. So let me introduce our UnICom solution. Based on our key insight, we introduce universal I/O completion, or UnICom. UnICom includes 3 designs. The first 2 designs is to overcome the tranche 1 and 2. It leverages various kernel infrastructure to overcome this tranche. The first design, including the TagSched design, it is a light-phase sleeping and wake-up mechanism, and TagPoll is an efficient and safe polling I/O completion approach. It can handle I/O requests from different processes and different steps, and it is running in the kernel, so it can provide safe and efficient and cross-process process service for all the requests. And the third challenge, we use the shortcut kernel I/O path, or skip, to address. This skip module, it combines a library file system and kernel module. This design is to provide a kernel running space for our previous designs, TagSched and TagPoll, and let them to efficiently to access some kernel resources. For example, like we build an extension. The extension maps the file offset to a corresponding block address in the file system. This allows we can translate file requests to block requests. We also manage many hardware MEM queue in the skip, and so that the TagPoll can directly to access this MEM queue and can chat and complete the I/O in high efficiency. We will detail the design of the TagSched design and TagPoll design. You may find the detail of the skip design in our paper. Then let me introduce the TagSched design. Its full name is Tag Guided in Queue Scheduling. This design is very simple. When an I/O step submit an I/O, we just give a tag, and this gets stored in each step's PCB, or there is the task struct in Linux. We just add a field to stop it. And when the I/O step submit this I/O, we tag it as I/O wait, and then the scheduler will skip the tag step, so that it will not this I/O step waiting for I/O will not get scheduled. But design is to in our design, instead of moving this tag step away from the one queue, we choose to retain this tag I/O step in the CPU one queue, so that we can avoid the high overhead of queue operation, so that it can reduce software overhead in doing the sleep and wake up mechanism. The last one is preemption, because we notice that based on this design, from the scheduler view, it is a computation intensive step. And so that if there's a compute C straps is blocking this straps. The IO strap have to wait for the whole time slice of computation, and you know that the time slice of C strap is very long. It is million seconds level, so this will resulting in very extreme long latency for IO straps. So we need to decide this preemption to preempt the C straps once the IO is completed. And the second design is the TagPoll. TagPoll means the tag notify polling. It will be, in this design, we first introduce a centralized system-level polling-based completion straps, and it will assign to a dedicated core. It will receive all IO requests from user-space application, and this strap is running in the kernel, so it can receive all requests and handle all multiple processes safely. And the second design is the low-cost wake-up. It is very simple because this completion strap will trap the NVMe queues, and if there are IO requests lying in the NVMe queue, they will check this state of this IO, and if the IO is completed, the strap will untag the corresponding IO strap, so the CPU scheduler can detect this IO strap and wake it up. So in this way, we can efficiently implement lightweight and low cost IO completion mechanism. And the third design aims to optimize the existing performance. That is the adaptive completion policy. It means that we will the TagPoll will direct commit to check the CPU load of each one queue, and if the CPU is idle, they will directly use the pure polling IO, and if the CPU there are many tasks on the same CPU, they will use UnICom IO. In this way, we can maximize the IO performance. So let me introduce the experimental environment. And we use 3 baselines, ext4 bypass D, and now using in SQ mode. For the baselines, we use 16 E cores to run it. And for our UnICom, we will reserve 1 core for the dedicated IO completion strap mentioned in the previous slides, and the remaining 15 cores used for application. First, let me see the pure IO workload performance. For average IO latency, we can see that we improve the interrupt performance on 4KB IOs by 42% with 1 strap, and we also reduce its latency of ext4 for 128 KB IO by 70.4%. And VS polling, we achieve similar performance because in this scenario, the adaptive completion policy is employed because in this scenario the CPU load is not heavy. And if we see the P99 tail latency, for 1 strap we improve the tail latency of ext4 by 31% for 4KB IOs. And for polling, we avoid the polling extreme long latency because you can see the polling tail latency P99 tail latency on 128 KB. It is over 10,000. We just make it to find around 600,000 due to our tag schedule design, lightweight sleep and wake up mechanism. And let's see the missed workloads for C-strap. And for this performance, we can see that the IOPS performance on 4KB IO UnICom outperform other solutions due to our TagPoll and TagSched design. And if we look into the 128 KB IOs, we can see that the C-sharp performance of UnICom does not drop as polling, but it maintains a consistent gap as interrupt because we reserve a CPU core for dedicated strap. And if comparing with the polling, we outperform polling both on IOPS performance and C-sharp performance because we address the mutual interference and the longer and longer bit waiting time of polling, so that we outperform on both 4KB IO performance and the C-sharp performance on 128 KB IO. And UnICom does not drop, continuous drop. This drops like the polling in C# performance. So let's recap our goal. Our goal is to under different CPU utilization, UnICom can show robust performance over different scenario. And the figure shown in the left side prove that UnICom achieved our goal. And in real-world application, and if we comparing with the single chip and 32 chips, UnICom have outperformed the ext4 and polling on the single chip performance, and very significantly outperform the interrupt. And for 32 chips, we primarily outperform the polling because we address the mutual interference issue. So let me make a simple conclusion. And in our paper, we analyzed the impact of existing IO completion mechanism across different workloads. And we introduced TagSched, a live-based sleep and wake-up mechanism, and the TagPoll, a centralized system-level polling-based IO completion mechanism for fast IO responsibly, efficient CPU usage, and multiprocess support. And Skip, a framework to efficiently bypass most of the kernel IO stack. And our evaluation showed that UnICom shows robust IO performance improvement across different types of workload. Thank you for listening. I'm happy to take questions.